Good morning, ladies and gentlemen. Today is the final physics flight of 15th TYPT. So I would like to start the final flight section now, and starting from introducing all the members on the stage. And then today we will, our schedule is a little bit different from the regular physics flight. Usually, opponent will challenge the reporter for problem, but today, reporter already choose their problems, so we will start our schedule from preparation phase. Okay, so I would like to start from introducing the jurors, and then all three teams on the stage. So, how about Professor Jia?
Hi, good morning.
Hi, good morning, everyone. I'm Professor Jia, a physics professor of Department of Physics, National Taiwan Normal University, and I hope this fight I can learn more. Thank you very much. Thank you.
Hi, I'm Xian Zhonggao from National Taiwan Normal University. This is the first time that I attend this final fight. I'm glad to be here.
Okay, good morning, everyone. My name is Wen Xinlin from National Taiwan Normal University, and I hope everyone enjoyed this morning.
Hello, I'm Hu Mingguang from the National Taiwan Normal University, retired. I hope everyone has a good day today.
Good morning, everyone, including those in there. I'm Xiangfang Cai from Physics Department, National Taiwan University. I hope everybody has a good time today. Thank you.
Good morning, everyone. I'm Zheng Yonghong from Department of Physics in Nangang University.
Good morning, everyone. I'm Mohan Li from Shida Pudong. Hope everyone enjoys the moment. Okay.
Good morning, everyone. My name is Dr. Xie. I'm from Academia Sinica Institute of Atomic and Molecular Science. Thank you. Good morning, everyone. I'm Cui Fu, come from National Taiwan Normal University. You have a good life. Thank you.
Good morning, everyone. I'm Sami Guo from National Central University. Thank you.
Good morning, everyone. My name is Fang Yulo from National Taiwan Normal University. I wish everybody have a good, enjoy the morning. Thank you.
I'm Yongyan Xu. I will be the chairman of this morning section. I'm from Taiwan Normal University. So then I would like the reporter, captain, to introduce your team members.
Good afternoon. I'm the captain, Wei Yue from Human Software. These are my teammates, Zhang Yubei, Li Guanxian, Chen Yingtai, and Lan Shaochen. Thank you.
And opponent team, please.
Honorable jury and fellow competitors, I'm the team leader from Team Galileo, and my name is Hong Bingwei, Zhang Weixun, Cai Renfang, Lin Shiyang, and Bo Yuan.
And last one, the reviewer your team.
Okay, hello everyone. I'm the leader from Team Epsilon from Kaohsiung Senior High School, and my name is Xu Yizhen, Xie Haorun, Qiu Yude, Wang Lishen, and Li Haozhe for my memory.
Okay, thank you.
Okay, just as I already mentioned, the problem already been chosen. So this morning, the first section, the problem to be used would be number 2, oscillating sphere, presented by L. Fire. So now I would like the clerk to start. We will start from the preparation of the reporter for 5 minutes. During the preparation phase, reporter please write down the presenter's name on the paper. Okay, the preparation time is almost up, so reporter, please start your presentation for 12 minutes, please.
Honorable jury's fellow competitors, this is a reporter from Human Sphere, reporting problem number 2, oscillating sphere. Problem statement, the light sphere with the conducting surface is suspended from the thin wire. When the sphere is rotated about its vertical axis, by twisting the wire and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. Due to the problem statement, I believe that we should focus on the investigation, how damping effect acts on the light sphere, and how do different parameters, for example, the size of the sphere, magnitude of magnetic field, etc., affect the motion of the sphere. This is the outline of our presentation. First, for my preliminary experiment part, I'll use my observation video to demonstrate the phenomenon. In this part, I'll focus on the qualitative explanation about how this phenomenon is caused. And next, I'll introduce my theoretical model regarding the Ohm's law, Gauss's law, Poisson's equation, and moment of inertia. Next, my experiment parameters include the magnetic field, induced angle, and conductivity of the sphere. Last, I'll talk about my conclusion. Preliminary experiment. This is our experimental setup. First, we use a thin wire for about 50 centimeters to suspend this conductive sphere. Next, we use a Helmholtz coil with 130 rounds to provide a uniform magnetic field inside the system. And this is how we measure the conductivity of the sphere. Through this formula, we are able to know that this is a cross-sectional area of the conductive sphere. And also, this is the electric current of the sphere. And these are general formulas for the potential difference in the electric resistance of the sphere. And through having two electrodes to test the electric resistance of these two parts, we can then get the R inside here. And then we can know the sigma, which is the conductivity of the sphere. Next, in order to verify that we are able to use this formula inside our experiment, we actually tested 100 data points for the surface between the coils to measure that the magnetic field inside this part can be, the amperes that we are giving to the Helmholtz coil can transform into the magnetic field can be assumed as this. And after verifying, we found out that by giving the Helmholtz coil a 2 amperes of electricity, we can get that it's about 1.55 millitesla. Through the observation video, you can see that from the left-hand side of one is the one simply rotating, while the right-hand side of one is the one rotating with the Helmholtz coil. From this chart, you can see that it causes a significant damping effect when a uniform magnetic field is added inside the system, and this is the damping effect. Next, I'll first explain about the torsion pendulum. We're giving an angular displacement for this conductive sphere. It causes a restoring torque to try to make it restore back to the equilibrium position. However, it does not stop in the equilibrium position. It actually rotates to the other side and keeps repeating this motion until it stops. And the reason that causes its damping in this condition includes the air resistance and refriction at ECU suspension. In a normal situation, when you're using a conductive outer shell, the sphere rotates about its vertical axis, while these conductive particles make circular motion, which causes a really thin electric current in this part. However, in our experiment, since we know that the charge distribution is restricted between the T, which is the shell of the conductive surface, and when thickness of the conducting surface T is way much smaller than the radius, then we can know that the radius component here can be ignored. Next, I'll explain about how eddy current is formed inside this system. So So today when a Helmholtz school is giving a uniform magnetic field from the left-hand side to the right-hand side, and since we know that the metal flow is basically an integration of infinite 2D coils. So in this part, I'll explain the metasphere by using this 2D coil. So when this 2D coil is rotating about its counterclockwise direction, then it causes from Lenz's law, we can know that it causes the contact area for the magnetic field to increase, and then causes the eddy current to rotate in this direction. And this is how eddy current is formed inside the system. And through the eddy current, we know that the I inside the Lorentz right-hand law. And also we know that the magnetic field inside the Lorentz law given by the uniform magnetic field. So through Lorentz right-hand law, we can know that there's always a Lorentz force going in the opposite direction where the matosphere is trying to rotate. And this is why it causes a significant damping effect when the system is rotating with a Helmholtz coil or a uniform magnetic field. Next, introduced by theoretical model. So this is the general formula of Ohm's law. And so what we want is a current density J. So since we already measured the conductivity, which is a sigma here, first we want to know about the magnitude of V cross V. And after derivation, we know that V cross V equals to this part. And in our theoretical model, we're using the coordinate system. So these are the coordinates. Next, since we already know V cross V, from Gauss's law, we are able to know the rho T, which is the charge density. And after inputting back into this formula, and through Poisson's equation, we can then get the phi T, which is the electric potential here. And after inputting back the phi T into this formula, we can get the electric field and back into this part. So since we already know the F, which is the Lorentz force here, we can then get the torque inside the system. And after derivation, we can know the angular acceleration and also the decay time, which we set as delta equals to 4 rho F divided by sigma mv squared. And the oscillating spirit declares is exponentially, which the angular inside our theoretical model, we set the omega as the oscillation frequency. So it is proportional to E powered by negative T divided by decay time. Next, experiment. So after comparing our theory line with our experiment data, we found out that our data actually decays faster than the theory predicts. It is because the original theory is only considering the damping caused by magnetic field, but it ignores some of the parts. For example, the damping caused by friction, air resistance. So in order to make corrections or modifications for a theory, we actually need to conduct an experiment without the magnetic field. And then by fitting, we can know that there's a damping coefficient without the magnetic field. So the damping coefficient is gamma inside this. So after combining damping coefficient with the original magnetic field damping coefficient, we can then get the correct theory. So after modification, we can know that this is a theory line with the frictional force added. First experiment that we conducted is by changing the magnetic field. We changed the magnetic field by giving different amperes for the Helmholtz school. And through this formula that we proved we can use, we actually, by increasing the amperes given for the Helmholtz school, we increased the magnetic field from 0 millitesla to 1.6 millitesla. And we found out that when the magnitude increases, the decay time of the angle decreases, and the rotational frequency will be constant. So after comparison with after turning all these maximum angular into absolute value, we can compare it with our theory line. So we can find out that there's actually much deviations when it's only 0 millitesla given from the Helmholtz school. It's because that most of the damping inside this line is caused by air resistance and also friction at suspension, which means that it is more related to the initial condition of the releasing, which causes the bigger deviation. Since most of the damping are not caused by the magnetic field. And from this formula, we can know that when changing the V here, it causes the decay time to decrease, which causes when the decay time decreases, it causes the system to have a more significant damping effect. The next experiment that we conducted is by changing the induced angle. And this is the oscillating axis for the wire. And so we want to know the horizontal component of the magnetic field. So when it's perpendicular to this axis, it actually has the biggest, when it's 90 degrees, it actually has the biggest this part, and causes the decay time to be smaller. And from this, we can know that when induced angle increases, the decay time of the angle decreases, and the rotational frequency also is the same. And that is because we make the decay time in this part to decrease. The last experiment that I conducted is by changing the conductivity of the sphere. I changed the material for the conductivity and put the conductivity sigma into this part. And so when the sigma is greater, it causes the decay time to decrease. And due to the low conductivity of the phenomenon, so the bronze, we actually changed two different materials, which are iron and bronze. And because the bronze is having a low conductivity, therefore the phenomenon is actually not apparent. In conclusion, by modifying the theory, which adding a magnetic, this is the original theory, it only has a magnetic force damping coefficient. By modifying the theory with new damping coefficient for friction, we can make the theory line to fit with our data as well, because we modified it. And for the first experiment that we conducted, we increased the beta, we increased the V, which is the magnetic field here. And it causes the decay time to decrease, which causes a more significant damping effect. And for the second experiment that we conducted, which also found out that the decay time of the same angle increases and the rotational frequency will be constant. And it is because that we make the decay time period smaller, which causes a more significant damping effect. And for the last experiment, we changed the conductivity, and because the bronze conductivity is really low, so the phenomenon is actually not apparent. And this is my conclusion.
Sorry, time is up. Thank you.
Thank you.
Now, opponent, please ask question to the reporter.
Okay, thank you for your presentation, and I have a few questions about your reports. First, please turn to page 5. The one that shows your preliminary experimental setup with a coil and a sphere. Okay, so is the coil you use here a hand-pulled coil?
What can you rephrase?
Is it a hand-pulled coil that you use in your experiment?
Yes, I'm using a hand-pulled coil.
Okay, so what is the relative size of your sphere and the coil? Your relative size of the radius of the sphere and the radius of the coil.
I didn't measure the radius of the homeschool.
Okay, thank you. You answered the question.
But the radius of the manosphere is 10. The diameter is 10.
Okay, thank you. Now please turn to page 24. Okay, so here you mentioned the difference notation of gamma and delta, and can you briefly explain what the two notations stand for?
Which part?
Yes, in your equation, you have the notation gamma and delta, and can you briefly explain what the two parameters mean?
The delta is the decay time, which means that the decay time is a definition when, for example, this is 100%, and decay time is when it reaches to 37% of the original amplitude.
Okay, thank you.
So
And what is the notation of gamma?
What is the rotation?
What is the notation of gamma? What does that mean?
Rotation of alpha.
Notation of gamma. What does that mean?
Notation of. Sorry, can you?
You have theta naught E minus gamma T minus T over delta.
Gamma. Sorry, gamma.
Yes.
So gamma is the friction coefficient, damping coefficient. Friction damping coefficient.
Okay, thank you. In your theory, did you write down an equation of motion you predict in your theoretical one?
Please turn to Ohm's law bar.
Okay, thank you.
Okay, time is up. Now is the preparation time of the opponent. Time is up, so opponent please take the stage for up to 4 minutes. The remaining time will be added to the discussion.
Okay.
So please start.
Honorable jury and fellow competitors, I'm the opponent from Team Galileo, and today I will be opposing question number 2, oscillating sphere. And this is the problem statement. And we believe the main focus of this investigation is how the magnetic field can affect damping effect and affects the motion. And the main focus of the reporter's report is the damping effects on the sphere and the different parameters affects the motion of the sphere. Okay. And for the theory part, the reporter used multiple rules in electromagnetic, such as Ohm's law and as we demonstrate in our presentation, and eddy currents and Lorentz force. And for the experiment parts, the tools, they use a Helmholtz coil to create a relatively stable magnetic field, and they use a wire and a sphere to create the situation provided in the phenomenon. And for the parameter, they change the magnetic field, and they also change the induced angle, and they also have mentioned the effects caused by the conductivity of the metal. And for the analysis, they use the chamfer for oscillation and rotational analysis. And they also mentioned the conception of the energy decay, and they introduced relevant parameters like gamma and delta, and they use the exponential function to describe this phenomenon. And for the conclusion they reached, the first one is when the magnetic field increases, then the K time also decreases. And the second one is when they change the induced angle, the rotating frequency is a constant. So here are some strengths and suggestions for the reporter. For the pros, first of all, is to measure the magnetic field by using the formula in a model of the Helmholtz coil. And the second one is the detailed experiments which demonstrated in their videos. And the third one is they can explain when does the damping come from, which is explained in their theoretical model. And the fourth one is they consider the air resistance by combining vector gamma into the resistance constants. And for the suggestions, first of all, we believe that in the presentation we did not see a theoretical equation of motion derived from a theoretical model which describes the relation of the effects caused by the magnetic field. And the second one is there was a quantitative comparison between the theory and the experiments. And the third one is like parameters, like changing the direction of the eddy currents, which believe that the reporter did not mention in his presentation. And also in the presentation, the reporter mentions that the model of the sphere can be viewed as a permutation of the coils being put together, and this one will be in our later discussion. So these will basically be the outline of our later discussion. For the first phenomenon, we will discuss the damping effect, and we will discuss where the damping effect comes from, and why can a magnetic field exert such effect on the sphere. And for the theory parts, basically these will be the points of discussion, and also we like to derive equation of motion from the expression of the magnetic torque provided in the reporter's presentation. And that's the end of my presentation. I'd like to start my discussion with the reporter now.
Reporter, please get down to the stage, and we start the discussion now.
Okay, now please turn to page 7. Okay, so here, can you briefly explain what this graph stands for?
What this graph stands for?
Yes.
Also, we measure 100 data points per Gauss's meter, so in order to prove that...
Can you say, can you speak slower, please?
Oh, we measure 100 data points between the surface, for the surface between the coils, and we use Gauss meter for the measuring of the magnetic field between the surface. To prove that we can use this formula, for example, by giving a 2 amperes of the electric current here.
Yes, and this formula is based on the assumption that you use a Helmholtz coil. Yes.
Yes.
Okay, thank you. And now please turn to page 10. Page 10. Okay, so here you have a conductive outer shell, and can you tell me what the material it is?
We're using iron and also But we're using iron and bronze for the material.
And what is this conductivity? As mentioned in your presentation, that the conductivity can affect the motion.
One of the conductivity for the smaller one is 37.08 times 10 powers of 6, while the other is 63.01 times 10 power of 6 Siemens per meter.
Okay, thank you. So here you have the outer conductive outer shell, then I want to ask what is your inner parts of the shell?
What can you rephrase the last one?
Okay, so let me rephrase the question. For your sphere, only the outer part is conductive.
Yes.
And what is the material of the inner part?
It's the same, like it's the same material, but it's hollow sphere.
Okay, thank you. And okay, so now please turn to page 12. Okay, so here is your explanation that you think that we use the word. That a conducting sphere can be viewed as a permutation of many rings, like this. Is that your point?
It's actually like duty coils like rotate in one, like in the same axis, so it can be integration of duty coils.
Okay, so here you introduce the conception of a coil. So now can you tell me what is the direction of the eddy currents in your theoretical model?
So as I explained, so for example, today this conductive sphere, metal sphere, is rotating about its counterclockwise direction, so it rotates in this direction. So we can assume that it is a 2D coil rotating in a counterclockwise direction. And because that the area that contacts with the magnetic field here is increasing, and through Lenz's law we can know that when increasing, it also actually
based on Faraday's law, yes.
What?
Based on Faraday's law. That's how you determine the direction of eddy current.
Oh yes, so when it's counterclockwise, the eddy current looks like it's in this direction, as I mentioned.
Okay, thank you. So now can you turn to the page that shows your theoretical derivation. Okay, so in this that's why we'll just leave it here. And so in this example, which situation are you considering to consider a uniform magnetic field which is perpendicular to the rotation axis?
Oh yes, it's perpendicular with the rotating axis, and we're only considering a hollow sphere with uniform magnetic field given by Hawkins.
Okay, thank you. So now can you please turn back, and I will tell you when to stop. Just turn back. Yes, go on. Next. Okay, thank you. So yes, the last page. Here you say the oscillating sphere accelerates exponentially with omega is proportional to an exponential function. Is that correct?
Yes.
Okay. So, however, now please turn to the pages that show your experiments. Okay. So here you have the relation of the oscillating angle and time, and obviously in this example, excuse me. The direction of the omega as mentioned.
Oh, the omega inside is actually the rotational frequency of the oscillation.
Yes, but the omega, since the rotation, it may turn in the other points, which means that under some occasion, it can go down where the omega is smaller than 0. However, in your theoretical derivation, which omega is proportional to an exponential function, which is always bigger than 0. So how can you explain this?
So it is rotational frequency, so the frequency will not be negative.
Okay, so can we define rotational frequency?
Frequency of this rotation.
So can you define this frequency?
How can I define this frequency?
Yes.
Like it's related with like e powered by negative t divided by the k time.
Okay, so now okay, so.
And where's the negative part that you're seeking from?
Yes, because in my opinion, the omega here is not the rotational frequency, it's the angular velocity.
No, but as I mentioned, we identified that as the oscillation or rotational
Okay, so
frequency.
now can you give a definition of rotational frequency?
Also, rotational frequency is like when it oscillates back to equilibrium position.
That is a period.
Yes, like the frequency of like this.
Okay, so in your definition, when it comes back, like here, okay, so here is your theta and t graph. So this is a period.
Yes.
So your definition of frequency, is it like this? Because I haven't heard what is your qualitative. Yes, so that is your experience. Now please turn back to the page of your theory. The last page. Yes, so here you have the notation partial omega, partial t. But as you just agreed, that your definition of the angular frequency is 1 over t. But t in your graph are these values. So which means that it may not be a continuous function. However, you differentiate it with respect to time. And here you have tau equals I delta, which I believe you should write tau equals I alpha, which means is a rotational form of Newton's second law. So this partial omega partial t should be the angular acceleration. So if this formula is correct,
yes, I agree. Like this part is angular acceleration. I like accidentally.
okay, so here the omega has to be angular speed. If this
No,
alpha has to
omega is like the oscillation frequency, but
if it is an oscillator frequency, you differentiate it with respect to time, then it is not the angular acceleration.
And this part, I mean, it's potentially related to this part. It's because I'm talking about the damping. It's under damping. It's the under damping situation that has the exponential.
Okay, thank you. I think we have to move on to next parts. Now, can you? So now you have the relation between the tau equals to this term, and where we can see that from here, that the torque is proportional to omega. Is that correct?
Yes.
Since all the rest is a constant. So, I'd like to ask that how can you derive your equation of motion from this expression?
You want to discuss the mathematical parts inside this?
Yes, I will discuss the mathematical parts of your presentation.
So I would like to suggest like discussing about my experiment data and also like not.
So you don't want to discuss the mathematical parts of your presentation?
Yes, because.
Okay, so let us move on to your experimental results, please. So now I'd like to ask another question about your experiments. Can you mention again what is the relative size of the radius of the sphere and the radius of the Helmholtz coil?
The radius of the sphere is 10. The diameter of the sphere is 10 centimeters. Well, I do not remember the radius of the. Oh, you mean the radius?
Yes.
Actually, I didn't remember the radius, but we calculated that. But
okay, so please turn back to page 5. The one that shows a preliminary, yes, this one. So from this observation here, we can see that the size of your sphere.
This is like demonstration. It's a model.
Okay, so do you have a real picture for that?
It's my picture.
Do you have a real picture of
this
this?
video? Sorry. Observation video part.
Okay, so here this is the size of your coil and this is the size of your sphere, right?
Yes.
Okay, so here I think that since your size of the sphere is not relatively really small, and I think that maybe you have to make sure that it stays in the center, because even if it's Helmholtz coil, the magnetosphere is not always uniform.
Make sure that it's in the center.
Sorry, time is up.
Okay.
So, opponent, please summarize the discussion for 1 minute.
From a previous discussion, basically we had a discussion over the theoretical parts of the theoretical model. And in the experiments, the opponents believes that the reporter did not understand the notation of the experiment, since he mentions that the omega is the angular frequency. However, he differentiated with respect to time to show that the value of the angular acceleration. So the opponent believes that the reporter should understand the theoretical model of in his presentation more. And as for the experiment parts, we believe that the Helmholtz coil size is not relatively big to the sphere, which means that under some vacation, the magnetic field, which has a flux over the sphere, may not always be uniform. So the reporter believes that the opponent can improve his experimental setup by making sure that the size of the ball is relatively small to the Helmholtz-Coyle's radius. That's my presentation. Thank you.
Okay, thank you. So now is the time for the reviewer to ask questions to the reporter and opponent. Please.
Okay, thank you for reporter and opponent and the reviewer of the discussion. And first question, I would like to start with the problem statement. So due to a problem statement mentioned that we have to use a thin wire, so what is the purpose? Because you didn't mention about it.
Referring to the thin part. So the reason why we should use a thin conductive sphere is because that from calculations we can ignore the radial component here because that the thin electric current caused by this conductive surface can be then ignored.
Okay, I understand. And how about opponent?
Can you repeat your question?
What is the purpose of a thin wire?
What is the purpose of the wire? Since if a wire is really thin, which means that we don't have to consider the mass
Okay,
compared to the
I
sphere.
understand.
Sorry, I'm glad you did that.
Sorry, I would like to ask another question about the problem statement. So, why do you use a hollow sphere instead of a solid one?
So sorry, I misunderstood your last question. I was explaining why we use a hollow sphere.
Sorry, I would like to move to the next question. So why do you use a hollow sphere instead of the...
Like the last answer I answered because I misunderstood.
Okay.
It's because that...
Well, I think it's mainly because when it is not a hollow sphere, then there may be some inner eddy currents that might affect the motion.
Okay, I'm going to move on to the theory. So due to a reporter didn't measure the radius of the coil and the sphere, so...
I did measure, but I did not like...
what if the coil radius is smaller than the radius of the sphere? What will happen?
So it provides a non-uniform magnetic field since it will not go through all of the whole sphere.
And how about opponent?
Since I think if the size of the ball is not relatively small to the radius, then the magnetic field the ball experience may not be uniform.
Okay, I understand. And did you take the thickness of the ball into the consideration?
Oh, it's like 0.1 centimeters.
Okay, so what will be different if we change the thickness of the ball?
Well, if we change the thickness of a ball, we increase the possibility that there might be some inner eddy current that is not on the surface.
Okay, and how about, do you agree with the opponent?
I agree with the opponent since when the radius of the thickness increases, it causes the electric current inside the thickness T to increase, which might impact the eddy current.
And I'm now going to move on to the experiment part. So the reporter mentioned about the size of the material. However, when you change the material, the density will also change, so the mass will also change. Do you think the mass of the...
changes the moment of inertia too.
So do you think the mass will affect your result?
It changes the moment of inertia, so it will affect
Okay, how about opponent?
Well, changing the inertia, which means you change the tau equals IW, you change the I.
So which kind of result do you think will change?
Yes.
Which kind of result?
Which kind of result?
Yes.
For example, the angular acceleration that the ball experiences.
So you mentioned that the damping is caused by the friction.
Sorry, time is up.
Thank you.
Thank you. So following is the preparation time of the reviewer.
for reporter and opponent, and I'm the reviewer of this session. Today I'm going to review question number 2, oscillating sphere. So here's the problem statement, and we may focus on a light sphere and white thin. However, the reporter and the opponent didn't mention about what is the purpose of the white thin. So we think that is have to be taken into consideration. And then, okay, and here's the summary of the reporter's presentation. So they may focus on the effect of the magnetic field and also the magnetic damping in the motion. They mentioned about the friction and also the air resistance. And the theory is that the Ohm's law and the Gauss's law and also the eddy current. For the setup part, they use a coil and also the conductive sphere and a thin wire. For the parameters, they said it's about the different material, different magnetic field, and also the induced angle. And for the conclusion, when the magnetic field increases, the damping will increase, and when the conductivity coefficient increases, the damping will increase too. So here's the pros and cons of the reporter. So they complete quantitative phenomenon explanation and a lot of experiments to prove the assumption, and also have a good experimental setup. The reviewer think is pretty good. And also, however, they didn't measure the ratio between the sphere and the coil. And the concept that makes of the quantitative comparison between the theory and the experiment, and unclear graph explanation didn't show the blank experiment for the original damping and could explain the mechanism behind the damping more, and didn't measure the radius of the coil and not familiar to the research of based on. So here's the pros and cons of the opponent. The opponents took a polite and calm discussion about with the reporter, and also clarified the theory that is misused on the blackboard, and also understanding of the reporter's report and clear presentation about his own opinion. And also give some appropriate suggestion about the reporter's report, and that reviewer believes that is really appropriate. However, the content that make of the discussion about the experimental setup and result, we may talk about the theory. So here's the discussion point. So what's the ratio between the radius and the coil of the sphere? However, the reporter answered that they measure the radius of the sphere, but didn't measure the radius of the coil. The reviewer thinks if the radius of the coil is smaller than the sphere, the magnetic field will not be uniform. And the opponent asked about, can you give a definition of the omega? And the reporter answered that we define as a period. However, a reviewer thinks the definition of omega should, in the report's research is kind of indifferent. And another discussion point is that the opponent asked about how did you make sure the magnetic field is uniform? The reporter answers that we measured it. And the reviewer thinks the radius of the sphere seems familiar to the radius of the coil. The magnetic field will not actually be uniform. And here's some best points the reviewer would like to mention about. So the first one is that the reporter didn't measure the radius of a coil. So the reporter can make sure the magnetic field they provide is completely uniform. And this is pretty important in this experiment because they use the theory how to be uniform. And also, the reporter didn't explain the method they changed the induced angle, and also didn't consider the thickness in the change in the theory. And also, when change the different material, the momentum of the inertia should be taken into consideration. And however, they didn't consider about the mass when they change different kinds of material. So this is all the presentation of the reviewer. I think, thank you for the reporter and the opponent's discussion part. Thank you.
Okay, thank you. Following is the reviewer makes the remark, please.
Hello, jury's fellow competitors. This is the reporter giving a concluding remark for the previous discussion. First of all, for the theoretical equation of motion, it is calculated in our theory. However, I do agree with the opponent that the tau equals I alpha bar t is time into delta. So, however, it does not affect that this understanding for the opponent towards the rotational frequency that he misunderstands. And the theory lines comparing with experiment results in every chart so that we are able to compare with the theory if there are any deviations. and the direction of any current can be predicted. Related to the metal sphere can be considered an integration of infinite 2D coils. So for example, today the metal sphere is rotating about its vertical axis in a counterclockwise direction. Eddy current on the surface looks like this direction. So we are able to predict the eddy current's direction. And the radius of the Helmholtz coil isn't significant. However, we measured it. But as you can see in our observation video, the radius of the Helmholtz coil is absolutely way much larger than the radius of this part. So as long as it's larger than this radius, then all of the magnetic fields can go through straightly through this ball. And however, the reviewer and the opponent kept saying that it causes a uniform magnetic field that might affect. But from observation video, you can see that the Helmholtz coil is way much larger than this little metal ball. And a Hall sphere is used because the thickness of the surface is way much smaller than the radius. Since we mentioned this conductive surface might cause a thin layer of electric current. So when this is thin enough, then the radius, the electric current will be small that we can ignore, which will not affect the main reason of the eddy current that will not affect the average eddy current. And as the size of Helmholtz coil is smaller than the radius, the magnetic field causing the sphere will decrease and slow down the
Sorry,
Thank you.
time is up. So I would like all three presenters stay on the stage and ready to answer the question from the jurors. So any questions? Yeah, please use the microphone.
The reviewer raised an interesting question that is missed by the reviewer. You didn't do the experiments for the size of radius of your sphere and in this field or not. Do you want to comment on what is the size effect on the eddy current and the motion?
So the size is bigger, which means that the cross-sectional area is larger. So the surface for contacting with the magnetic field will increase. So the eddy current on the sphere, if it's larger, then the eddy current will increase. However, the moment of inertia will also increase. So I'm not able to predict, like, if I know the radius or also the moment of inertia, then I can predict how damping is affected, or the decay time.
So for the reviewer, could you comment on if it's field or not, and what's your idea on that?
Well, I think the eddy current is vertical to the magnetic field. So could you please ask the question again? Sorry.
If the two spheres have the same conductivity, one is field, one is not field. Just now you were asking him the same question, and what is the comment on that affecting the AC current and impact on the motion?
Okay, so the eddy current will vertical to the magnetic field, so it will cause a jerk that may cause the resistance.
How about the opponent? Do you have comment on those questions?
Excuse me, can you restate the question?
I asked the two questions. Do you have comment on either question?
Do you mean the equation that I mentioned?
Sphere that has the same conductivity. One is bigger sphere, one is smaller sphere.
Well, since if we consider the model given in the reporter's presentation that he used a ring of a coil as a permutation to modify the sphere, then I believe that the cross-sectional area will affect the magnetic flux and therefore will change the value of the induced current.
Any further question?
In order to verify that the magnetic field is uniform, you did major field, right?
Yes, I use
And the region is it larger than the, say, volume of the sphere? Did you make sure of that?
Which volume is?
The sphere is supposed to be in a uniform magnetic field.
Yes.
And you didn't measure the core radius because you say you just measure the magnetic field to verify that it's uniform, right?
No. We did measure the radius of the Helmholtz coil, but...
No, that's not important. My question is, you measure the magnetic field and make sure they are uniform.
Yes.
And the region of uniformity is larger than the sphere. Is that correct?
Can I explain, like briefly explain how we measure?
No, my point
Yes,
is...
that's correct, that's correct.
Okay. The question is, did you verify the field around your sphere is uniform?
Oh, yes.
Yes or not?
Yes.
Yes. So that should settle some problem. But I think the key problem is a very difficult aspect of this problem is the what you call eddy currents and induced angle. You only include, or your derivation only shows the induced currents effects. It provides a let's say
Sine B, like
the current is, because it's rotating this way and the current is going like this, so it creates a magnetic field in the y direction. X is the rotation direction and B is the z direction. And that, of course, is an effect which slows down the rotation. But this second it creates a magnetic field in next y direction. Originally, you have a z direction. This y direction, after being induced, is also in the rotating. It's also in a rotating conductor, right? So it should generate an effect, and that is also an eddy effect, eddy current effect. Is your induced angle related to any of these two? But because I didn't follow your induced angle, what does that mean?
So the induced angle means the angle for, so this is the rotating axis, and the induced angle is the angle between the harmless poles, the magnetic field given through this. So by changing the induced angle, like the same sine B increases. So I also agree that when changing an induced angle, it might cause different eddy currents in different directions. However, we're not able to measure the charge distribution on the sphere.
Okay, I think Professor already got your answer. I think a short question, maybe two. One, two.
A basic question for all three fields. How does the damping change the simple harmonic motion?
How fast it changes through harmonic motion?
Just change what? What is changed?
What is changed? You mean from different parameters or?
Simple harmonic motion, you have you can characterize a simple harmonic motion by what? And then what does change?
You mean how causes the damping?
Yeah, when the damping factor is change, what is changing in your oscillation?
The decay time is how we define that the damping is.
Yeah, short. We have time is already over, so short answer,
So
please.
the decay time is changing.
Okay.
And I believe that the amplitude of the motion will decrease due to damping.
Just that. Okay.
I think the simple harmonic motion will acting like the torsion pendulum.
So, is that okay? Yeah, please.
So I would like to check what kind of material you use. I mean your metallic ball. I heard that you use eyebrow.
Yes, but it's actually not like.
Okay, so a short question. If the size is the same, but if you use, for example, eyebrow and copper, do you think there will be a different result?
It depends on the conductivity. So for the smaller conductivity, it causes the decay time to increase. So it is more like unsignificant.
Okay. Yeah, further? Okay, thank you. So we move on to the scoring part. Okay, seems the score already been given, so please show your mark to the reporter. So pronounce, which way I should pronounce? This way or this way? Okay, I start from my right hand side. It's 6, 7, 8, 9, 9, 6, 8, 7, 7, 7, and 8. And the scores for the opponent, please. 5, 7, 8, 8, 9, 8, 7, 8, 8, 8, and 8. And the scores for the reviewers is 6, 6, 8, 8, 9, 8, 7, 8, 8, 7, and 9. So I would like to ask some short comments. Maybe start from the reporter. We have 2-9 and 2-6. Any comments from the 9? E and F.
Somewhere over there.
Yeah, short comment. Reporter, presenter, can you stand up and because the comment is to you.
I think your report is very excellent, and you have a good description of phenomena. But I think you should quick answer the opponent very short. And when you done this, I think you will get a high score.
Yeah, you want to come in? Well, okay, that's okay. So we have 2-6. One is from.
For the report, I think there are some key issues that are really
I don't think it's wrong.
The magnetic field is not uniform. The only uniform is in the middle part. So your sphere is bigger than the middle surface. So it is not uniform. That is one. And second is that it is a pity that, as a reviewer mentioned, that you didn't measure the natural frequency of the oscillating without magnetic field. That is a very big drawback. So that you don't actually know how the damping effect on the oscillations. And also one key point is that is the magnetic field only induce damping. So could it start the rotation? That you didn't mention anything about that. So I think, but actually, on the other hand, you did a lot of experimental work, and the data is really nice, so that you have a little bit average. So that is 6.
Excuse me.
Yeah, please.
I think the uniformity
It's not necessarily in the center. It's almost all the way to where the coil is. Penhole's magnetic field has this special feature, so that's why it's used quite often. It's not just in the center.
Okay. So then, for the please.
The reason I
Ask that did you measure the magnetic field, and is it uniform? If you did measure it, and you make sure that the uniformity covers the whole sphere, then that's it. Of course, the uniformity is not theoretically uniform, but the error should be very small. I think that's the key point in doing this experiment. Other things are not important. The uniformity, you measure it.
Sorry, I think you don't have to. We we can just make comments and discuss with the students later. Yeah, because the time is limited. So, okay. For the opponent, we have a single 5 and single 9, 2 7 and a lot of 8. So maybe start from the lowest mark.
Okay. So for the opponent, there are two parts you didn't perform well. First is that for the questions. It's not a number, but I think the first two questions is too technical, which does not help to clarify the report. For example, you asked about the radius. So that is not helping. And secondly is that during the discussion, actually, I don't see the priority, and also some of your questions couldn't connect together to help us to understand what actually happens there. For example, you first asked if the magnetic field is in the middle, and then you asked about the material, and very late you asked about the size, but we don't know if all the questions combined, how could that lead to deeper understanding of the topic. Therefore, for these two parts, you got lower grades from me. For example, for the question and ask, you got only 0.7. And for the discussion, you got only 1.5 from me. Otherwise, you should be better.
Okay, we have a 9. You want to comment? If you don't want to comment, we can ask other 8. It's okay. So, any professor giving 8 want to give some comments? No? Yeah, please.
I think that everyone should know that basically simple harmonic motion is modified by linear friction, so that it changes amplitude and period and omega both. I think the opposer spent most of time asking about the omega. We got this error in the reporter's report that omega is proportional to exponential. This should be the amplitude proportional. We correct it later, and then we spend too much time asking about these things, and then you regret the subsequent discussion. That's all.
Okay, thank you. So for the reviewer, we have the lowest mark is 2 6, and 1 2 7, several 8, and 2 9. So would you like to give some comments? You give the 6. Yeah, please.
Actually, for the review, drawback is that you didn't actually review the opposition speech. So otherwise, it's a fair review. And also, additionally, is that the review of the reporter, the report is a little bit too, without key points. So you mention everything, but I think here you need to highlight the key points. So basically, otherwise, as I mentioned, it's a fair review.
Okay, we have 9 from Professor Jia. Can you give us a short comment?
I appreciate there's a female student on the stage. That's the first thing I have to say. And secondly, I think he has a very good strategy plan. Although I agree with Professor Law about his presentation in the beginning, didn't completely cover all the discussion among between the reporter and the opponent. So that's why I give her 9 points. Okay.
Okay, thank you. So the first round will close here. We will have a 10 minutes break. So please get back to the seat in 10 minutes, please. Thank you.
大的要不要？